Yeah, so last time we were talking about stoichiometry and really kind of combining the two things that we talked about previously, which is really our grams to moles and our balancing of equations. So again, these are calculations that you could do from equations to figure out all kinds of things, as long as you know one piece of information. So if you know how much reactants you're starting with, you can figure out how much products you should produce. If you know how much products you produce, you can go back calculate and figure out how much reactants you started with. You can stay on the same side of the arrow as we talked about. If you know one reactant, you can figure out how much of the other reactant you need. And same thing with the product side. If you know one of the products, you can figure out how much of the other product you would produce as well. For our class, pretty much all stoichiometry type problems boil down to 4 basic steps, and that is none of it works, as we talked about, unless you have a balanced equation. So you do need to have a balanced equation. Again, if the equation is given to you, you should take a good look at it to make sure that it is balanced. The next thing you want to do is take whatever they give you and basically convert to moles. So very commonly, that is a grams to moles conversion. And usually that, again, is the molar mass from the periodic table that allows us to do that. Once you do that, the third step really is the stoichiometry step. And remember that from a balanced equation, we could take the coefficients and come up with really the mole to mole relationships. For example, 2 moles of A, give me 4 moles of B in this example as one of the relationships. There's actually 3 different relationships. And from that, you can write 2 conversion factors like we talked about the other day, where again, we can set up our problem in dimensional analysis and solve for what we're looking for. And the third step is to go to that balanced equation and find the mole to mole relationship of what you are interested in. And for our purposes here in this class, you'll be interested in whatever they gave you. And then obviously you'll be interested in whatever you're trying to find. So those are really the 2 things that you want to kind of find from that. You're going to use that again as a conversion factor, and that's really all stoichiometry is a conversion factor that we get from a balanced equation, and that is why you got to make sure you balance it. Yeah, so you'll make sure you always balance it in that case. Once you do that, you should be in moles unless you did something wrong. And usually on the back end here, we got to do some other conversion to take it to some other unit perhaps. And very commonly on the back end, we go moles to grams a lot. And again, that would require the molar mass from the periodic table. It really is just these 4 steps in order. If something is done for you, then you just kind of skip ahead and don't go backwards. And it should get you to the end spot of where you need. Any questions on that? All right, so we finished up on 1, I believe. So let's take a look at the second part of that question, which I think is this. So using the same equation, I think on the one we finished up on last time, in this case, we want to know how many grams of H2 can you form by reacting 81.75 grams of lithium with water. Again, a couple of numbers from the periodic table. Lithium 6.941. Hydrogen there 1.008. I think that might be all you need. I'll throw oxygen in there for free. 16. All right, so follow those 4 steps and see what you come up with. Again, balance equation, convert to moles, mole to mole. Okay, let's take a look, see how we're doing. So once again, trust me when I tell you, just follow these 4 steps. So let's do that. We want a balanced equation, which obviously we already did in the previous step of this problem. So we do have a balanced equation, so that is checked off our list. In this case, that's the only piece of information given to us. Do I need to convert it to moles? I do. It's in grams, right? So I got to take it from grams to moles. So this is where the periodic table and the molar mass comes into play, which is that number on the bottom. We take about 4 significant figures, and that means that there are 6.941 grams per mole for lithium is the molar mass. We again could use that as a conversion factor. So the number always stays with grams, is always 1 mole as our conversion factor. So the second step here, we'll take our number, 81.75 grams of lithium. Again, going to set it up dimensional analysis so we can see everything cancel. So grams need to go opposite here, which means we do need to put the grams on the bottom and a mole of lithium up on top. At this point, the grams of lithium would cancel. If you want to get an answer at this point, once again, you don't necessarily have to, but if you like to, I'm going to get an answer just because we're doing step by step here. And once again, I'm not going to round too much at this point because I do have other steps to do. And I should probably write the right number would be good as well. That's probably helpful. Let's try it again. 11 point, looks like 77784 will go, moles of lithium. So that takes care of converting it to moles. The really reason I need to convert it to moles and get it into moles in that second step is that's really the basis of stoichiometry, is a mole to mole relationship so that everything cancels out correctly. So what I want to do now is go to my equation and find the 2 things I'm interested in. So clearly lithium is one of those things. And we are looking at hydrogen as well. So we're going to get the mole to mole relationship from that, which is 2 moles of lithium. Gets me out 1 mole of H2. Once again, that is nothing more than just the coefficients. So there's no math. It's just simply the coefficients in that balanced equation. That gives me 2 conversion factors I could use, 2 moles of lithium over 1 mole of H2, or 1 mole of H2 over 2 moles of lithium. So continuing on with my number here, I'm going to take my 11.778, I feel like I missed a 7 there. Put it in there, 784 moles of lithium. Once again here, this is the big stoichiometry part. We want to get rid of lithium, which is on top. So again, we want to go opposite. So we're going to use the conversion factor there on the right, which will be opposite of where we have lithium right now. So 1 mole of hydrogen, 2 moles of lithium. That is the big stoichiometry step right there. That cancels out the moles of lithium divided by 2. Once again, I'm going to take it to a few digits here, 5.8889 moles of lithium. So once again, this comes from the periodic table. It's the molar mass, which is our conversion to go from grams to moles, moles, grams. This comes from the balanced equation, which is our stoichiometry. And is that the answer that we're looking for here? Or not? We're looking for grams. So we do have to do step number 4. It's also really important to write the right thing. So I'm going to scratch that out and put H2 right there, which is what it should be in this case. I just want to make sure you're paying attention. Maybe. All right. Just wrote the wrong thing. One of those things could be true. So now that we are converted to H2 in this case, we do need the molar mass of H2. So again, we need to go back to the periodic table and get the molar mass of H2. And that is basically 2 times 1.008 grams per mole. And that's going to give us 2.016, I believe, grams per mole for hydrogen. Again, we're going to use that as a conversion factor to finish out the problem here, 5.8889 moles of H2. Here we want the moles to cancel, so we're going to put the moles of H2 on the bottom, the 2.016 grams up on top so that they cancel. And that will end us with here about 11.87 grams of H2. And that would be step number 4 here. So once again, I did get an answer after each step, which, as I mentioned before, you could just do it all in one sort of calculation all together. If you do pretty much like I did there, take it to a few extra digits and then clean it up at the end. The sig figs would be based once again on the only number that we see there, which is pretty much that one, which is 4 significant figures. And that is what we end up with. Any questions on any of those steps? So what does this number really mean? This number really means is if you did this reaction and you threw in there about 81.75 grams of lithium, everything went perfect. There was no side reactions. You weren't a klutz that spilled anything along the way. You should get out exactly 11.87 grams of H2. So that is what is sometimes referred to as the theoretical yield, which is based on the equation, the maximum amount of product that you could get out. A yield can only be a product. So in this case, since H2 is a product, that is why it's sometimes referred to as the theoretical yield. In reality, when you do a reaction, there's always stuff left behind. So you never usually get 100% yield when you do it. Any questions on any of those steps there? All right, so let's try another one here on our way to professionalism here of stoichiometry. All right, based on this equation, you're starting with 765 grams of C6H12O6. How many grams of CO2 will you produce? I'll give you some numbers here. Carbon is 12.01, hydrogen 1.008, and our oxygen there is still 16. All right, give it a go. Follow the 4 steps. Even if the equation looks scary, still follow the 4 steps. Doesn't matter. Okay, let's take a look and see how you're doing. So once again, we're just going to follow the same 4 steps, regardless of the equation. Everything looks kind of scary, but we do see some numbers there. If you did check it, it is balanced, so that's good. So we don't need to do that step. Step number 2, which is our convert to moles. Again, the only piece of information given to us there is 765 grams, which means we do need to do that. And once again, we do need to go from grams to moles. So we do need to use the molar mass from the periodic table here for C6H12O6. So adding up all the parts here, there's 6 carbons, each at 12.01 from the periodic table, plus 12 hydrogens, each at 1.008 grams per mole from the periodic table. Plus, I'll go underneath, there are 6 oxygens, each at 16 from the periodic table. And that gives us a molar mass for this compound here of 180.2, I think, grams per mole. If I'm not mistaken. Any questions on how I got that number there? Once again, we're going to use that as a conversion factor here. So we'll do our step number 2, which is 765 grams of C6H12O6. Once again, we want to get rid of grams. So we're going to put the grams on the bottom, which is 180.2 grams per mole of C6H12O6. The grams at this point will cancel. And once again, if you did get a number here, if you chose to kind of get a number, you would have something like 4.24528 moles of C6H12O6. That again comes from the periodic table, our molar mass as a conversion factor. Now that we have it in moles, which is really the purpose of stoichiometry, is to use a mole-to-mole relationship, we're going to do step number 3, which is go to the equation, find the 2 things we're interested in. So clearly they gave us some information about this guy, so we're interested in that guy. And we want to find CO2, which is over here. So those are the 2 things we're interested in. And once again, we're going to get the relationship, which is nothing more than just the coefficient. So that means 1 mole of C6H12O6 gets us 6 moles of CO2. That again gives us really our 2 conversion factors that we could use in this problem. Our 6 moles of CO2 over 1 mole C6H12O6. So to continue on, we'll take our 4.24528 moles of C6H12O6. We want to get rid of that, which means we are going to use a conversion factor here on the right because they are opposite of each other. That gives us the 6 moles of CO2 up on top and the 1 mole of our C6H12O6 on the bottom. Those guys are going to cancel. So basically just multiplying by 6 at this point gets us something like 25.471, I'll call it 7 moles of CO2. This would be our answer if we wanted it in moles, but we don't want it in moles. We do want it in grams. So we do need to go one more step, which is to convert those moles into grams. That's going to require the molar mass from the periodic table. And it's important to remember at this point, though, we are now at CO2. So we do need to go back to the periodic table and get the molar mass of CO2. We can't use, obviously, the same number we used at the beginning. And that means for CO2, there is a carbon at 1201. And there are 2 oxygens, each at 16. Going to give us a molar mass for CO2 of like 4401 grams per mole. Once again, we're going to use that as a conversion factor here to do our very last step. So continuing on with our non-rounded number here of 25.4717 moles of CO2. Here we want the moles to cancel. So we're going to put the moles on the bottom and the grams will go up on top. Again, that comes from our periodic table. The moles of CO2 will cancel, finishing this by multiplying this by 4401. Going to give us about 1,121 grams of CO2. Significant figure wise, really the only number we got going on here, which is 3. So maybe like 1120 grams would be good. You know, if you got the time for the sig figs, you should maybe do something like that. So hopefully, again, you can kind of see some of the pattern here that it is just the same 4 steps. So don't overcomplicate it. Just follow the same 4 steps and it should get you again to the end. Remember that if something is done for you, you go forward. If you don't need to do something, don't do it. Yeah. So like on the very last step, if you needed just moles, put a box on it. Yeah. And clean it up. Sig figs. Don't go any further. Any questions on any of those steps there? Once again, as I mentioned, you could really just kind of leapfrog from here to here to here and do it all in one calculation without getting the intermediate answers. But again, if you do get the intermediate answers, not a big deal. Just don't round too much. Yeah. Any questions? All right. One last one here to confirm how good we are at this now. All right. So got even a scarier looking equation. So how many grams of cisplatin? Molar mass 300.1 grams per mole is obtained from 0.7752 grams of K2P2Cl4 molar mass. They were nice enough to go to periodic table for you, so you don't need any of that there. So those are the numbers that you need from the periodic table. All right, follow the same 4 steps. Okay, let's take a look. So once again, a lot going on here, but ultimately we're looking for the grams of this guy here. So this is basically what we're looking for. This is the molar mass from the periodic table. So instead of adding up all the parts yourself, they were nice enough to give us that. We are starting with 0.7752 grams of that guy. And once again, instead of looking it up yourself on the periodic table, that is the molar mass from the periodic table for that guy, which we're going to use as a conversion factor, obviously, in this case. Clearly, if it wasn't given to you, just like we did in previous problems, you would need to go to a periodic table and add up all the parts yourself there to get those numbers. So we want a balanced equation, which it is. We want to take what they gave us, which was this guy, and convert to moles, which we do need to do. And in this case, they were nice enough to go to that periodic table, like I said, and kind of do it for us. So that is the kind of the second step we're going to do. Use the molar mass that was given to us. We're going to put the grams part on the bottom so that it cancels. And at this point, if I stop, I have I have moles of K2PtCl4. In this case, I'm not going to get an answer. I'm just going to do it all in one calculation so you can see again how it works. At this point, I am on step number 3, which is the mole-to-mole relationship. So once again, we're going to go to the equation, and we're interested in what they gave us, and we're really interested in what we're trying to find. In this case, it is a 1-to-1 relationship from the equation. So for every 1 mole of the guy we started with, and that's the coefficient, we get 1 mole of the longest formula known to man here. There you go, 2 in that case. So the next step that we want to do, and again, setting this up dimensional analysis wise, we see that the moles of the K2PtCl4 are on top. So opposite to get rid of it. So we will go 1 mole of the KT-PtCl4 on top, 1 mole of what we are looking for as our final guy there on the top there, and then a guy on the bottom. This is really step number 3 here, the mole-to-mole relationship. That's going to cancel out the moles of what we're not interested in, and that's going to leave us moles of what we are interested in this case. That is close to what we need, right? If we stopped right now and got an answer, we would be in moles, but we do again want grams in this case. So we need to do that 4th step. And once again, if it was not given to you, you would need to go to the periodic table and grab that molar mass from the formula yourself. And we're going to finish the calculation here by doing the 4th step, which again, the moles want to cancel. So the moles of this guy will cancel. And that is 400, not 415. It is actually right here, 301 grams of this guy. The moles will cancel. Now we're in grams of what we're looking for. And if we do the multiplying the top there, that's going to be 0.7752 times basically 300.1 hit equals, and divided by really the only number on bottom there, 415.1. Going to get us 0.5604 grams of our product here. So as you can see in this example, once again, I didn't get answers after each step. You could put it all together and just do it in one kind of continuous calculation. Or again, like we did previously, you could get answers after each of those steps, obviously, as well, if you wanted to. Any question on stoichiometry? So hopefully, again, you can see it's just the same 4 steps. Yeah, so just repeat those 4 steps. One last reminder, as we talked about last time, and I think as we did today, you could do stoichiometry from reactants to products. You could do it from products to reactants. You could stay on the reactant side and do stoichiometry, the same 4 steps between 2 reactants. You could also stay on the product side and do it between 2 products. So you could use these 4 steps and the balance equation really to figure out anybody in the equation, as long as you have one piece of information. Any questions on stoichiometry here? All right, that wraps up chapter 7. Okay, we're going to pick up here chapter 8, which should be the last chapter on exam number 2, which is, you know, coming up at some point, I imagine. Let's see. Maybe like 2 more weeks from Wednesday or something like that, in that ballpark, I think. Not Wednesday, not this Wednesday. Don't send me the email, but it's 2 weeks. Go 2 weeks from Wednesday, I think, and then you might be there. All right. So gases here, obviously in this chapter, and talk about gases, which is a state of matter where at that point, everybody has broken apart from one another and they are bouncing around, they are flying around. There's lots of collisions that occur, collisions with the container, which we associate pressure with. So as they're banging around, they cause pressure, which is typically related to gases. So let's talk a little bit about substances that are gases under normal conditions. And when we talk about normal conditions, that's really sort of everyday conditions. So like usually we think about temperature being 25 degrees Celsius and pressure being 1 atm, which is an atmosphere, and that is a unit of pressure. So under normal sort of everyday conditions, ionic compounds really don't exist as gases, and that's really because ionic compounds are ions, and ions are held together by really strong electrostatic attraction, positive, negative attraction. It's kind of like one of the strongest attractions you could have, which means they're just going to kind of stick together. They typically will not go into the gas phase. In order for somebody to go into the gas phase, you need something held together not as strong, and they're able to sort of break apart from one another, the different molecules, so they can start flying around as they gain energy. So typically speaking, when we talk about ionic compounds, they typically are not found as gases under normal conditions. Frankly, you could heat the heck out of those things and they will just start to melt before they will go into the gas phase. So it takes an enormous amount of energy to even try to pop it into the gas phase. In normal conditions, that just doesn't happen. It will, like I said, start to really melt beforehand. On the other hand, though, if we look at molecular compounds, and these are guys that basically share electrons, they are a little bit different than ionic compounds. There are certain ones that do come as gases, so that's carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, and methane. But a lot of molecular compounds are liquids or solids at room temperature. The difference, though, is between an ionic compound and a molecular compound is it's like a lot easier to get the molecular compound to go into the gas phase. The very simple example is water. Yes, it's very easy to go into the gas phase. So you can make some pasta, right? When you heat it up, it starts to steam, right? And it gets water in the gas phase. And that's because unlike an ionic compound, which are basically stuck together through that really strong electrostatic attraction, when you have two water molecules, they are also attracted to each other. Oxygen is more negative in water, hydrogen is more positive. So when you get a couple of water molecules together, the negative side of one and the positive side of the other will be attracted to each other. And this is what is known as an intermolecular force. And that is a force that holds two molecules together. And that is different than really what is referred to as an intramolecular force. So for example, if you took just one water molecule, those bonds where they're sharing electrons, those covalent bonds, are intramolecular forces. They are the forces that holds one individual molecule together so it doesn't fall apart and become alphabet soup. Yes. So when we have two water molecules together, it's held by an intermolecular force. And if that intermolecular force, which is always weaker, these forces are always weaker than the intramolecular force, are always stronger. And something like an ionic bond, electrostatic attraction, is actually an intramolecular force, which again is why it doesn't fall apart. We know that the intermolecular force is actually weaker because when we do heat up water in our example there to make pasta, we don't get hydrogen gas and oxygen gas, right? And if we did, that would mean that these bonds are weaker. That would get us the hydrogen gas and oxygen gas, which you'd never get to the pasta part. So that doesn't happen. What actually happens is you break this bond between this water molecule and that water molecule, which allows them then to go off into the gas phase. So when we heat something like water, it's the bond between the different water molecules, which is actually the weaker bond. And that's the first thing that breaks when we hit something like the boiling point of water at 100 degrees Celsius. And that allows those water molecules to separate. The individual water molecules are still able to stay together because those individual bonds where they're sharing electrons are much stronger and obviously will not break apart at 100 degrees Celsius. Otherwise, like I said, it would be a mess if you try to make some pasta every night. The general rule is the stronger the attractive force between one molecule and another, and itself really, the less likely you're going to find it at a gas phase under normal conditions. That is why things like, for example, methane are gases under normal condition. Methane is held together by a super weak force, so weak that it doesn't take much but looking at it and it will separate from each other, and they are gases. A lot of the early organic molecules, as we'll talk about when we get into organic chemistry, are like that. Methane, butane, propane, right? Those are all gases, as you maybe have used some of those, right? To barbecue or whatever it may be. But they're non-polar molecules are held together by what's referred to as dispersion forces. And dispersion forces are intermolecular forces, but they're pretty much the weakest you could get. So it doesn't take a lot of convincing to get those guys to go into the gas phase. That's also why when you work with organic molecules, which are usually non-polar, they have you usually do it in the fume hood because they're very volatile, which means it doesn't take a lot for them to, even if they're in the liquid phase, to jump out into the gas phase and give off fumes and stuff like that. So that's why when you get into those labs later on, you'll do those things, some of those things in the fume hood. Yeah. Yeah, intermolecular force, yeah, is a dispersion force. So dispersion forces are, there's really, I'm sorry, intermolecular forces, there's really three of them. The water example is what's known as hydrogen bonding. It's a bond between hydrogen and another guy. Dispersion forces is what nonpolar molecules typically use as intermolecular forces. And then polar molecules use what is referred to as dipole-dipole, which is another intermolecular force. Those are the three types of ways that basically one molecule interacts with another molecule. The strongest of all of them actually is hydrogen bonding. The dipole-dipole is really strong, and dispersion is super weak type of force. And basically hydrogen bonding is for polar molecules that have a hydrogen attached directly to an oxygen, nitrogen, or fluorine. So in water, the hydrogen is directly attached to the oxygen. So it creates a really polar bond and allows them to interact with each other. Dipole-dipole is for just straight polar molecules that cannot hydrogen bond. So guys that don't have that hydrogen that's attached to anybody. And dispersion forces are strictly really for non-polar molecules and stuff like that. So I think we'll revisit that in a little bit later chapter as well. Yeah. Other questions, or maybe we did in an earlier chapter, I think one of those. All right. Now, substances that normally are found as gases under normal condition, we have our diatomic molecules like hydrogen, nitrogen, oxygen, and fluorine and chlorine. Ozone, which is O3, is a gas. And then obviously our noble gases, which are monoatomic, which means they come as ones. So that is our helium, our neon, our argon, krypton, all the ons, xenon. These are our guys that are chemically inert. And again, they do come as ones. So looking at the periodic table there, I made this one day when I was bored, should get a hobby, but these are all the guys that are gases under normal condition when you look at it under the periodic table. All right, so let's talk a little bit about a gas and a vapor and the difference between the two. A gas is a substance that under normal conditions, it comes in the gas state, basically. A vapor, on the other hand, is something that normally is not in the gas state under normal conditions, but can be converted to it. So our example of water is a very common example of that. Water is normally a liquid, but you can convert it into the gas phase. And that's why we sometimes refer to this as water vapor rather than water gas, because it sounds funny when you say water gas. So water vapor is how we refer to it sometimes. And that is a substance that normally is not in the gas phase, but can be converted into it, is basically what a vapor is. And a gas is like hydrogen gas, oxygen gas. Those guys normally under normal conditions by themselves will come as gases. Now a barometer, which was invented by a guy named Torricelli, is a apparatus that is used to measure pressure. And old barometers, much nicer picture on the next page, but old barometers used to have a pool of mercury and a tube in it. And basically the atmospheric pressure would push down on that, and in goes the tube, and the mercury starts to rise there in the tube. Mercury, by the way, if you ever see it, has an unusual meniscus. It actually goes the opposite way. So it actually goes upwards, mercury, as opposed to kind of the downward U like everything else. And You probably won't see it too much. They've taken it out of most labs. I think probably here as well. At most schools, they got rid of it because it had mercury in it. They have more like an alcohol sort of barometer in a lot of places these days. Some common unit of pressure, an ATM is an atmosphere. A torr is equal to 1 mmHg, and mmHg is millimeters of mercury, because on a traditional barometer like this, you have mercury and you usually had a ruler. And on that ruler, you could read where the mercury is at. A lot of times it's in inches, centimeters, or millimeters. So millimeters is sort of used basically when you look at it. So that's basically millimeters of mercury is what that represents. A torr, I'm assuming, is named after the guy that invented the barometer there. So we gave him his own little unit. 1 torr is the same thing as 1 millimeter of mercury. There are 1-to-1 conversion. And this is the 3-pack of conversions to go between those different units. 1 atmosphere is 760 millimeters of mercury, or 760 torr. That means if you have atmospheres, you need to multiply by 760 to get torr or millimeters of mercury, so that those guys will cancel. And if you have torr or millimeters of mercury, which is essentially the same number, you're going to divide by the 760 to get to atmospheres. Those will cancel and we'll get you atmospheres. So there also are other units as well, like PSI, pounds per square inch. There is pascals and kilopascals. There's also bar, which is kind of similar to an atmosphere, 1.01 to 1. But for us, atmospheres, millimeters of mercury, and torr are pretty much the 3 units that you will most likely come across the most. But there are obviously other units of pressure. Here's a much prettier picture of a barometer, but if you close your eye, my picture looked almost like that. You close both eyes and my picture looked even better, I think. All right, so again, we have our pool of mercury, and we see the kind of mercury going in the opposite way there in terms of our meniscus here. All right, so when we talk about gas laws, which we are going to talk about, there's really 3 sort of variables. We talk about P, which is pressure, V, which is volume, and T, which is temperature. So in a lot of these gas laws, we may keep one thing constant and vary some others. But those are the 3 sort of variables that we see a lot in these different gas laws. So we're going to take a look at our first one here, which is Boyles Law. And Boyle looked at the relationship between pressure and volume, and that kept constant temperature. So temperature was held constant in this arrangement here. Oops, come back. And really what Boyle found was if you had a fixed volume of gas, the temperature is inversely proportional to the gas pressure. So here's the idea, right? I have a volume that is smaller. So as the volume gets smaller, that means that all my gas molecules now are very close to one another and not a lot of room to move around, which means we would expect more or less collisions to occur. If we all jumped into one small closet, we're going to definitely bang into each other a lot more than we would in this big classroom, right? So in that very small room, in that very small volume, there's not a lot of room for those gas molecules to fly around. That's going to increase the collisions. And the more collisions you have, you then would see the pressure start to go up, right? So squeeze everybody into a small volume, a lot more collisions, a lot more pressure. The other thing that would happen, for example, though, if we increase the volume, so if we increase the volume, that now gives these gas molecules a lot more room to fly around, right? Which is going to take a little bit longer for collisions to occur. And because of that, we would actually start to see the number of collisions start to come down, right? Because they got a lot more room to fly around in before they hit something. And the result of that is we will see the pressure go down. So as one goes up, the other goes down basically here. It is such a constant relationship that if you take the same gas and you measure a bunch of pressures and volumes together, and you multiply the pressure times the volume and all these different numbers, they will always come out to the same number. They're constant. And that's how that relationship is. And because they are constant, we could actually set it up for two different conditions. This is Boyles' law here. And that is P1 V1 equals P2 V2. Once again, this is at constant pressure. P1 and P2 are the pressures, kind of like before and after, if you want to think about it that way. The units does not matter as long as they are the same unit. So they got to be the same unit on both sides for everything to cancel out. Yes, sir. I didn't mean constant temperature. It's kind of like my other thing I wrote wrong today. There we go. Thank you very much. Constant temperature here. And obviously with our pressure and volume is varying in this case. Thank you. So our two pressures there do need to be the same unit. It doesn't matter what unit they are as long as they are the same. And the same thing with the volume. It doesn't matter what unit of volume you got, milliliters, liters, whatever it may be. As long as they are the same on both sides, everything will cancel out correctly. This is a equal sign here, and a bunch of gas laws have equal sign. What happens when we move things from one side to the next? Across an equal sign, they end up in the opposite location, yes? So although it's not really a fraction, if I need to move P2 to this side, it ends up on the bottom, right? And if I need to move V1 to that side, it ends up on the bottom. Opposite locations, right, is multiplying and dividing when you do that. So when we look at a graph of Boyles' law, as we can see here, much smaller volume, much higher pressure. As we give everybody a lot more space to fly around in, we start to see the pressure come down. Again, the number of collisions should also come down in that case, as opposed to heading in this direction where we will see the number of collisions start to go up for sure, and that results in more pressure. All right, why don't you try one here? An inflated balloon has a volume of 0.55 liters. At sea level, 1 atmosphere, rises to 6.5 kilometers, where the pressure is 0.4, assuming. Okay, let's take a look at this, and I would highly recommend in gas problems, since there's a bunch of gas laws that you need to know, a lot of times it's really a good idea just to really pull out the information and kind of label what type of number it is, and a lot of times that will kind of point you to the right gas law to use. So doing that here, we definitely have a volume that is 0.55 liters. We have 1 atmosphere. An atmosphere is a pressure that goes with that. We have 6.5 kilometers, which is frankly useless information in here. So watch out for some of that. We have another pressure that is 0.4 atmospheres, and we are looking for a volume here. So again, if you weren't sure, and obviously we only have one gas law to start with right now, but later there'll be more. That should really point you to Boyles' law that we were just talking about. You can almost see Boyles' law there. Doesn't matter which ones you call ones and twos. The answer is no, as long as you keep the numbers that go together. So as long as you keep them together, most people just go by the way they are in the problem. So these are ones, these are twos. And our Boyles' law here is P1 V1 equals P2 V2. In this case, we are looking for V2, so we do need to move P2 to the other side. So once again, although it's not written as a fraction, you could think of it being over 1. So P2 to the other side means it ends up on the bottom, basically opposite location of where it started from. We're basically dividing both sides by P2 in this case. That would give us P1 V1 is P2 equals V2. Now we want to put in our numbers. The only thing we have to worry about here is our units, and we are good. Both of our pressures are in the same unit. Once again, if they are different units, you do have to do a conversion to get them to the same. Here we're going to put everybody in the right spot. So that's going to be a 1 atmosphere up on top. That's going to be a 0.55 liters divided by 0.4 atmospheres. Here, the atmospheres on top and bottom will cancel. That's going to leave us liters, which is good since we're looking for a volume in this case. So we're basically going to take 0.55 and divide it by 0.4, basically. And that gives us a 1.4 liters in this particular case. Any questions on that? Two significant figures, since everybody's got two significant figures and we're multiplying and dividing, so that seems good. Any questions on the calculation there? We also want to make sure that maybe it doesn't make sense. So what we know about Boyle's law here is, in this particular problem, our pressure started at 1, ended at 0.4. That means my pressure went down, right? Which means my volume should go up. My volume started at 0.55, ended at 1.4, so it did move in the right direction, right? So if you understand sort of the relationship that's happening, you could check to make sure, hopefully, that your answer makes sense, because sometimes people very commonly inverse numbers when they're doing these type of calculations. Any questions on that there? All right, so that's Boyle's law, pressure volume relationship. The next relationship we're going to look at is Charles' law, and Charles' law dealt with the volume and temperature relationship, and we had constant pressure here. There's also another relationship, which is our Gay-Lussac's law. He dealt with pressure and temperature and held constant volume. So let's talk a little bit about each of these and what's going to happen. First off, we'll do our constant volume here. So in the case of Gay-Lussac's law, we have pretty much a rigid container here, constant volume, which means that volume is not going to change. So when I have some gas molecules in there and I increase the temperature, the gas molecules are going to move slower or faster? Faster, right? Like the old saying, light a match under you, right? You're going to move faster, right? So it's going to start to move around faster, which means those gas molecules are going to fly around a lot faster, which means should I have more or less collisions? Should have more collisions, right? They're moving around faster. They're going to start hitting everything in their way. And that's going to result in us seeing the pressure start to go up. The volume's fixed. It's not going to do anything. It's just going to kind of stay there. Now, the opposite is true. If I lower the temperature, my gas molecules now will start to move slower, right? Less energy, which means it's going to take longer for them to start colliding with things, which means the pressure should then go down, right? Less collisions would happen, and we will start to see the pressure go down. So in the case of Gay-Lussac's law, as you increase the temperature, you see the pressure increase, and as you decrease the temperature, you see the pressure go down. He has a gas law, which is P1 over T1 equals P2 over T2. And once again, that is constant volume. Any questions on that? Now, let's talk about Charles' law, which is down here. V1 over T1 is equal to V2 over T2. In the case of Charles' law, we want constant pressure, which means when we take a look at this, and we got some gas molecules there, if I increase the temperature in this case, just like down here, and the volume doesn't move, we would expect the pressure to go up. But in this case, we want it to have constant pressure, which means what happens to the volume is it will actually go up and increase as you increase the temperature. And that is because the only way to keep constant pressure is to give these gas molecules that are now flying around faster a lot more room to fly around, right? So we increase the volume and we end up with the pressure remaining constant. The number of collisions remain constant. So in Charles' law, the way it's able to maintain constant pressure is the volume actually adjusts to give everybody enough room to fly around in so that we don't have more collisions than we had originally. Same thing happens in the case of Charles' law. If we lower the temperature, our gas molecules again are going to be flying around slower, which means we're going to have less collisions. So what happens in that case is the volume will once again adjust to a smaller volume, which means Now the rate of collisions, they have not a lot of room to fly around in. So even though they're moving slower, we're going to still have the same number of collisions, basically just kind of squish them together to keep the number of collisions constant, and we will see the volume go down. So in the case of Charles' law, the way it's able to really maintain constant pressure is the volume actually does the adjusting, and the volume does the adjustment, and that allows the number of collisions to remain the same, and that keeps us at constant pressure. We don't have that in Gay-Lussac's law. The volume is fixed, so it cannot adjust like in the case of Charles' law. And because there's no adjustment in that volume, the only option is the pressure's got to go up or down depending on how the temperature goes. Any questions on either of those relationships? Now, the volume in this equation does not matter the units, but the temperature does need to be in Kelvin for sure. And also over here in this equation, the temperature does need to be in Kelvin. Pretty much if it's a gas law and you have temperature, it needs to be in Kelvin. Yeah. So a reminder that temperature in Celsius plus a 273 gives us our temperature in Kelvin. Even in a question that you might come across, which is they give you the temperature in Celsius, they want the answer in Celsius. So people think, well, I could just throw it into the gas law in Celsius. You cannot. So you have to put it into Kelvin, go into the gas law, and then do the conversion on the back end. So definitely any gas law temperature, Kelvin. Pressure, though, on this one doesn't matter, again, as long as they're the same unit. So it's really the temperature is really important. The reason why pretty much in all gas laws you need the temperature to be in Kelvin is if you take any gas and plot volume versus temperature and extend the line to the temperature line, they all hit the exact same point, which is minus 273.15 degrees Celsius. That again is the number that we basically use to convert to Kelvin. And Kelvin recognizes behavior, which is why it used to be called the absolute temperature scale, then later called the Kelvin. Because if I convert this into Kelvin, plus 273.15 gives me 0K, which is absolute zero. Yeah, so that is why basically all gas laws has to be in Kelvin because of that relationship. And we do see what we were talking about as well, low temperature, small volume, higher temperature, larger volume. Again, that volume adjusting for Charles' law to keep the pressure constant. Any questions on that there? All right, let's try one here, I think. In an experiment, 452 milliliters of a gas is used to light for a light bulb. It goes from 22 degrees to 187. What is the final volume here? Okay, so let's take a look. Now we got a few equations. So we got Boyles P1 V1 equals P2 V2. We got Charles V1 over T1 equals V2 over T2. We got Gay-Lussac's B1 over T1 equals P2 over T2. So once again, if we pull out the information from this problem, we have a volume that is 452 milliliters. We have a temperature that is 22 degrees Celsius to another temperature that's 187 degrees Celsius, and we are looking for a volume here. So once again, by just labeling everything, it really should point you here as clearly there's no pressure to be involved with, and there's no pressure on this one. So again, you could hopefully find the right equation pretty easily. Once again, I'm just going to label these guys as ones, these guys as twos. In this case, we do have a little work to do here with our units as our temperatures in Celsius. And as I mentioned earlier, pretty much it's a no-brainer. It's got to be Kelvin when it's a gas law. So we're going to add our 273 to each of these. That's going to give us 273 plus 22. Gives us a 295 Kelvin. And we'll add a 273 to that guy there. Will give us 460, I believe, there, Kelvin. Now that we have everybody in the right units, we got V1 over T1 equals V2 over T2. In this case, we want to basically isolate V2 by itself on top. That means really for our T2, we need to send it to the other side. And once again, if you just want to do it quickly, it goes opposite there. So it's just going to go upwards there. We're basically going to be multiplying both sides by T2 in this case. That will give us V1 T2 divided by T1 equals our V2. So now we want to make sure that we get the right numbers in the right spot. So our V1 is 452 milliliters. We want T2 up on top, not T1. So we want T2 up on top, which is 460 Kelvin, and T1 on the bottom there, which is 295 Kelvin. Our kelvins will cancel. That's going to leave us units of milliliters as our answer. So that's a 452 times 460 divided by a 295er there. Going to hit us a volume of like 705 milliliters in this particular case. Yeah. First off, any question on the calculation there? Once again, we can think about our relationship. So this is Charles' law relationship where we have constant pressure. That means when we look at the temperature here, it did go up. And that means we should expect the volume to also go up, right? And that's what we see. It started at 452, ended at 705. So it did go up. Again, just a little wake and maybe check to make sure you didn't make a mathematical error, or might help maybe in that case. Any questions on that there? Now, another gas law that's important to lead us to a very important gas law is our friend Avogadro. So our friend Avogadro had a number, but he wanted a gas law as well. So when we think about Avogadro, that is 1 mole, right, is what we think about. So not surprisingly, his gas law involves moles. It is V1 over N1 is equal to V2 over N2. And this is actually at constant pressure and temperature. So 2 constants in this case, pressure and temperature. N is the moles. So N is the moles and V is volume here. So you can use this just like any gas law. And basically as the volume increases, so is the number of moles. They're sort of proportional to each other. So the moles go up, so is the volume of gas as well. And that's how, again, it keeps constant pressure in that particular situation. And vice versa. Obviously, as the moles go down, so does the volume as well to adjust. So I throw Avogadro's law in there. I don't know how many problems we'll do with Avogadro's law, because when we take together Boyles law, Charles' law, Gay-Lussac's law, and our friend Avogadro's law, we basically, when we put all these guys together, we get really the big gas law of the season, which is the ideal gas law. And the ideal gas law is really sort of a combination of all those laws together. It is different than all the other ones in a sense of all the ones up until this point are kind of 2 different conditions. You got 2 pressures, got 2 volumes, 2 temperatures. This is like a one and done. You got one of everything basically in this case. So the ideal gas law is PV equals nRT. This is also the most restrictive in terms of units. So when you use the ideal gas law, 100% of the time, the pressure does need to be in units of atmospheres. So if you're going into the ideal gas law, you got to have that pressure in atmospheres. The volume has to be in units of liters. And which we just talked about needs to be in units of moles, and no surprise there. Our temperature does need to be in, I'll write a K maybe there, Kelvin. And the reason for all that is R. R is what is referred to as the gas constant. And the value that we use for R is 0.08206. And it has units of liters times atmosphere divided by Kelvin times mole. Now, a lot of people these days will use 0.0821, sort of the rounded number, which is perfectly fine. I personally use the other number most of the time because that's what they beat in my head and I can't get it out as much as I try. So that's the number I use. But a lot of books now will kind of round it up there to 0.0821. So you can use either one, is perfectly fine. The other good thing is you usually will be given the R value, which means if you're not sure what everybody else's units are, they're right there. Yeah. So that'll tell you basically what everybody else's units need to be in when you use the ideal gas law. The ideal gas, and what is an ideal gas? An ideal gas is, unlike a fake gas, it's an ideal gas where basically there's two things that make something an ideal gas. One thing that makes something an ideal gas, as we'll talk about a little bit later on in this chapter, is the idea that the volume of the gas itself is relatively small to the container that is flying around in. So when we think about gases and we think about the volume of gases, and if you read a lot of problems, usually they'll refer to like the volume of the container the gas is in rather than the volume of the gas itself. So because it is flying around, it fills the container uniformly. We think more of the actual container's volume rather than the volume of the gas itself. The other major thing that makes something an ideal gas is under normal conditions, you can put as many gases as you want together. They pretty much will not interact with each other. So there'll be no forces where they'll be attracted to each other. There'll be no forces where they're repulsed by each other. It's almost like they're in there by themselves, which is a very important part of an ideal gas situation. And under these ideal conditions, you could have multiple gases in there and almost just go like, forget about the other ones. I'm just going to focus on this gas alone and not worry about any other type of interaction between the gases. That doesn't happen in really large pressures and really high temperatures. And in those cases, you do have to take into account actually the volume of the gas itself and the interaction between gas molecules. Those are sometimes referred to as real gases, which we do not talk about in here. We focus just strictly on ideal gases, which you basically don't have to take those two things into account. Yeah. I don't know if there's necessarily a relationship, a steady relationship like we see in the other ones. The other ones we see a steady relationship because they're basically both the same variables on each side. So that's why we could kind of see them go up and down. Here we don't have the same variables on each side. So there's not necessarily a relationship where you could go like every time the pressure goes this way, that type of thing in a sense. Although they are on opposite sides of the equal sign, so you could have a little bit of that relationship. Other questions?